This is my presentation for Lab 4 on circuits and capacitors. In this lab, we will be experimenting virtually with circuits to explore the time dependence of voltage from a discharging capacitor. This will be done with loop rule, node rule, and Ohm's law. In this video, I will first go through the fundamental principles for this experiment, then the series circuit observations, followed by the RC circuit observations and the analysis of the data gathered during that section, and finally some discussion questions. The first fundamental principle is loop rule, which states that the algebraic sum of potential differences in any loop must be equal to 0. The next is node rule, which states that the total current into a junction equals the total current out of a junction. And finally, there is Ohm's law, which says that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points. We'll also be using this formula which relates RC circuits and time. So here are the procedure, questions, and observations from the series circuit sections. I predicted that the I1 and the I2 currents would be 0.02A, and that is exactly what I measured. When I reversed the ammeter, the measurement did not change, and when a voltmeter was inserted, the ammeter measurement did not change, and the voltmeter read 3 volts. When I measured the potential difference across different parts of the circuit, I found that VA minus VB equals 3, VC minus VD equals negative 0.96, and VE minus VF equals negative 2.04. Every other measurement was 0, and in total these equal 0. This follows the loop rule. We were also asked to make a chart of the voltage across the different parts of the circuit. You can see for every part of the circuit where it was just wire, the voltage did not change. And across the capacitors, the voltage increased to 3 volts, and then across the 2 resistors, it decreased back to 0. The ammeter had no effect on the voltage. Here are the procedure, observations, and questions from the RC circuit section. Why doesn't the addition of the voltmeter change the reading on the ammeter? Very little current is able to actually flow through the voltmeter, so the circuit is changed very little and the ammeter is not affected. What happens if an ammeter is connected parallel to the 100 ohm resistor? Both ammeters read 0.06. What is the resistance of the different circuit elements? I calculated this with a formula that divides the electric potential by the current. You can see, for example, for the 47 ohm resistor, I divided the 0.96 change by the 0.02 current, which is constant for the circuit, and I got 48. When I repeated this for the 100 ohm resistor, I got 102, and for the wire and the ammeter, it is equal to 0. What happens to a light bulb when a battery is connected in an RC circuit? The bulb starts off bright and then dims to nothing. What happens when a light bulb is connected to a charged capacitor? The bulb once again starts off bright and then fades. What happens to the current in each of these scenarios? The current starts out large and then decreases to 0 over time. How long did the capacitor take to charge and discharge for 10 and 20 ohm light bulbs? When it was the 10 ohm light bulb, it took about 5 seconds to each discharge and discharge. When it was 20 ohms, it took about 10 seconds. We were also asked to gather data for various intervals of time and then the voltage at these times. When I plotted these in Excel, I generated a line of best fit, which we'll use in the next slide. So using the linearization formula from the procedure we were provided in the line of best fit from the graph, we can estimate RC. The slope of our line is negative 0.1457, which is equal to negative 1 over RC. And so with this, we estimate that RC is 6.86. We can also calculate RC by multiplying the known resistance and the current, which would be about 6. So our estimate is reasonably close. And here are 2 discussion questions. What if you were using an actual ammeter? A real ammeter would not have 0 resistance, which would decrease the current flowing through it, and any current we measured would be lower than predicted. What if you were using an actual battery and capacitor with no resistor? Our model would predict the capacitor would charge instantaneously because there is no resistance. In reality, it would charge quickly but not quite instantly because the battery and wires have little but not 0 resistance. Thank you.